So Ross has been talking very eloquently about sort of UK capability, not capability with maritime autonomous platforms that are out in the field now. Which is, mature technology, operational. I'm going to talk a little bit about sort of research end of it, the lower technology readiness levels, and the kind of things that are coming through next in vehicle technology that perhaps might influence the next generation of marine science activities and indeed other domains, military and offshore oil and gas as well. And at the heart is autonomy. So, and in autonomy and unmanned systems, it's all about the operator, unbelievably. So there's always an operator. There's an interesting, actually it's not just in marine robotics this is happening, it's happening in all sectors. So you'll be hearing about self-driving cars or reading about them in the news. There's stuff happening in manufacturing, in the nuclear industry. And the buzz line is that these new generations of robots affect everything that moves, in the same way that the computer revolution affected everything that uses data. This new robotics, smart robots that act as assistants in some way to people to make them more productive, have them not going into unsafe environments, dull, dirty, dangerous, that stuff, and it really is a revolution. It's going to change a lot of things, and even some things that don't move. I'm working on a project at the moment that's called IntelliTable, and it's getting a table to move around and bring stuff to you instead of you going to the table, which if you're disabled is great, right? That's what you need. And so we think about the sort of how the autonomy in three ways. The sort of manual control, which is the sort of ROV thing Gwen was talking about. There's shared autonomy, so where the operator is in some sense directly interacting with the system. They won't actually be controlling the actual degrees of freedom. There's some other thing going on in between. It's not a bit more than fly-by-wire because of the complexity. If it's a humanoid, how do you control the hand and stuff, or something that's non-anthropomorphic. But the bit we're interested in is what we call persistent autonomy, because the nature of the ocean, as we've been hearing, is such that it's hard to communicate. So if you take the umbilical cable off, the vehicle has to be able to make some kind of decisions for itself. And the sort of things that we try to characterize that persistent autonomy, operate successfully, limited recourse to the human operator, extended lengths of time, environments that are not completely known, adapting purpose in response to unexpected events and disturbances on different scales in space and time, whilst interacting with the environment, touching things, turning things, and recovering from errors in task execution. So if you don't know, the robot doesn't know the environment it's going into, unexpected things happen, it has to be able to respond to that. That's something that we all do very easily, but it's a big ask to get a robot to do it, to get a machine to do it, to write the code to get a machine to do that. So it's a big ask, but we're kind of making progress. And I wanted to kick off with this, I think, which is probably the best commercial example of what I think of a persistently autonomous robot that has some of those features in it. Sure, AutoSub is long range, but as Gwyn says, it's long range. It's a relatively dumb vehicle, so you can keep it going. This one is designed. It's actually being built and operated by Subsea 7. Seabite, one of our spin-outs, did the brain for it. It's doing commercial work for Shell at the moment in the oil field. It's designed to work around FPSOs, floating production systems, and in deep water to do all the inspection. So the robot has a map, a CAD model of the environment in it. It navigates mainly using sonar, actually. It navigates by servoing from the forward-looking sonar, looking at objects that it recognizes or parts of the structure that it recognizes. It updates its navigation based on that recognition. And it brings back data. So at the end of the day, the thing that's important actually isn't the robot, it's the data products that it brings back for the oil field. But it's persistently autonomous because it has some independent decision making. It's able to recover to a limited number of errors, and if it detects interesting events and anomalies around a crack, for example, in a riser, then it'll swim in close to get close-up video if it's seen something on sonar. So it has a limited amount of ability to readapt its mission on the fly. What it isn't able to do very, very well is deal with the unexpected. So if you put it into the Gulf of Mexico after Deepwater Horizon, when everything was a mess on the seabed, it wouldn't really be able to cope because it doesn't have a map of where unless you went and mapped it first and then gave it the basic planning. So that's quite an advanced system, but it shows you actually how far there is to go before we get to these persistently autonomous robots. We're seeing the first versions of them coming out, being commercially usable, but there's still some way to go. And the sort of things you have to get good at, I won't talk about them here, but robust control in the presence of disturbances, so using machine learning techniques actually not just for learning data and classifying and recognizing, but actually for controlling, for sticking it in the feedback loop to control the vehicle's behavior. So here we are with water motion disturbances and hovering in unusual attitudes, that kind of thing. This one's not running, I don't think. There it goes. This is Nessie, one of our vehicles in the Oceans Lab, and it pitches up and rolls around. It's quite hard to do, actually. There's a lot of nonlinear dynamics in there for those of you that are inclined on that kind of thing. Here what we're doing is giving the robot the skills. So if you want it to have these persistently autonomous behaviors, how do you give the robot the behaviors? Is it somebody sitting there at a keyboard typing away, trying to put in lines of code that tells it what to do? Well, you can do that. That's sort of a fairly dumb way to go about it. Here what we're doing is teaching the robot the skills. In this case, we're turning a valve. So this is getting into interacting between the robot and the environment. And what we do is we have an operator through a joystick demonstrate to the robot or the robot's brain how to execute the operation, in this case turning a valve, doing it 2 or 3 times. What the robot learns is a series of probabilities. It learns a Markov process, for those of you who are into that kind of thing. What it doesn't do is just learn a series of actions that you give it, or some set of motions that it has to do directly. Because in the presence of a disturbance, thinking about persistently autonomous robots, it wouldn't be able to offset that disturbance in quite the same way. And so what we're able to show here is that as a result of just doing 2 or 3 training runs, so not as many, but I mentioned earlier about machine learning in general needs a lot of training data. Actually, this one doesn't because of the way it's put together for action. I think you'll see that just on the right there behind the vehicle there's a propeller been switched on, so there's a big sea current blowing, and the robot's able to offset that and hold position, even though it wasn't taught to do that in the learning phase. And then we've applied that to other things. So what we're doing on the right there is an anchor chain cleaning activity. So you've got disturbance forces on the robot, which forces it to go backwards. And it's not a real anchor chain, by the way. It's in the lab. It'd be too heavy to have a real anchor chain, so it's actually made of plastic. But it looks like a real anchor chain. And then at the bottom, what we're showing is that if thrusters fail, the robot can still behave safely. It can still maneuver to the right point in the space, even though it might not be pointing in the same direction, rather than just going blindly off and heading off in different directions. So these are the sorts of technologies that we want to see embedded in robots so that they can carry out this task. Here's a final one. It's doing a mapping exercise. We're actually mapping the pier legs under the pier at Fort William on the west coast of Scotland at the Underwater Centre, which is where we quite often go. What's interesting about this isn't the fact that it's doing the mapping. Mapping's an easy thing to do. What's interesting is that it doesn't know anything about the environment that it's mapping when it goes into it, and it adapts the mission on the fly based on what it sees that's interesting that should be mapped. So it's getting back to this reacting to the mission, reacting to the task at hand, and being adaptive about it all. That's a step ahead. So that if you were trying to do a mapping operation around Deepwater Horizon, or indeed some of the sorts of things that we were hearing about earlier on, then with scientific phenomena, then you can adapt the behavior on the fly in order to do that. Change. We've heard about unmanned warrior and the various vehicle operations that are going on. I won't labour the point. We've got some of the assets as well, up at the Ocean Systems Lab, although we're not participating in the trials next week. In addition to actually one of my slides hasn't come out here. It has come out, right? I have to go back a bit here. The sort of thing we've been concentrating on is the sort of Internet of Things. So getting the numbers of robots to be able to operate in an acoustic network under the ocean. So rather than just doing point-to-point acoustic communications using HUI or Evologix modems or whoever it is, implementing things like a kind of Dropbox. We all use these kind of things to synchronize data across computers. We've been working on our Internet Things in an EU program, another EU program called Sunrise. We've got a little project in there called Mango. And what we're trying to do is synchronize the world models, the environmental models that the various vehicles have, so that each vehicle has the same kind of situational awareness of what's going on, and therefore they can collaborate together in order to work together in order to solve a task. And such is the nature of acoustic communication that there's a lot of delay, it's limited bandwidth, and a lot of packets get dropped. Right? And so really what you're trying to do is implement this sort of networking, this kind of Dropbox idea, in an environment where you have to prioritize what things do you sync first. So it has to be slightly smart that the most important things get synced first. In your Dropbox that you use on your computer, it's the smallest things that get synced first. And that's actually quite smart, right? But maybe that's not strategically the most important thing as far as the mission is concerned. And so there's some smart things that we do there in the way we do the networking. And then I haven't got an underwater video to show it because the underwater videos are a bit difficult to show. But here we're seeing an example. We're actually working in the lab, same software. We've got a drone that flies and a drone that drives along the ground. And the two are working together. The drone that's driving along the ground is trying to reactively map and navigate its way through the environment using simple Kinect sensor in this case. But it can't see everything, so it can't make the decision about which way to turn. What the drone does is go and map from above and then communicate back to the turtle bot, in this case the ground robot, what it should do. So that's an example of the kind of synchronizing. And it was great to see on Russ's last slide, Seabyte. You can buy this now, or some of it, not all of it. Seabyte has a product called SuTrack Military, and Neptune is one flavor of SuTrack Military. And it's been de-risked and worked primarily with the US Navy to start with for mine warfare, mine countermeasures. But it enables multiple vehicle operations to be doing search, classify, map, reacquire, identify. And I don't think we've done neutralize yet, where you actually go and blow the mine up. But there are systems out there that that purport to do that kind of thing. So some of this is in research, but some of it is actually out as commercial products. And the networks exist, the translational networks exist to go from research out to commercial application. Some of the other things we've been working on, just to sort of broaden it out a little bit, because of the lack of communication. You may not be, or for other reasons, you may not be able to communicate effectively with your assets all the time while they're in the ocean. And so how should you know what's happening? Autonomy is all about the operator. How does the operator know what's going? Some of the guys came up with a system they call the Back to the Future engine, going back to the movie. And the idea is that we run a model on the surface of everything that's supposed to be happening. In this case, it's just one vehicle, but you could do it with several. We've done it with several vehicles. And so what the operator gets is a prediction of what's happening under the water based on the mission plans that the vehicles have got. When some kind of connection is established, the vehicles upload, this is what I've actually been doing for the last 10 minutes, 20 minutes, or whatever it is. And then you resynchronize the displays so that what the operator is seeing is actually a correct hindcast of what actually went on, rather than some forecast of what might have been going on based on prediction. And actually getting the interface right so that when you switch from the predicted world to what actually happened, you have to do that quite carefully, because if you do a quick jump, then it leaves the operators their situation awareness goes and they become completely disoriented, right? So finding ways to do that. And then there's things like you can then slide the forwards and backwards in time to see what has happened in the mission in the past, what might happen in the mission in the future. And these are sort of the kind of things that when we worked with operators, the kind of things that they liked us to be able to do. And so, I said earlier on that there's a lot of developments happening with the vehicle platforms and making them persistently autonomous and giving them some of these smarter capabilities to react on the fly, to communicate, to work together, to plan missions together, to execute missions together. But actually the thing that's really interesting is the data. And if you look at where the oil field is going, they think about these vehicles not just as the vehicle platform. What they think about is the information architecture. So they think about, in this case, the oil field, the FPSO, as a smart space. And the drones are just a means to an end in that smart space, either to gather data or to be able to have some effect. Right? The really interesting thing is about the gathering of the data, the storing of the data, the reusing of the data, and the interfacing of the data to the operator, so that the right decision is made at the right time. So actually, it's wrong to think about these vehicles in isolation. You have to think about them much more in a systems context, because that tells you what the vehicle platform needs to be able to do in order to satisfy the requirements. Where's this going? And robotics in general. This is not an underwater drone. It's a humanoid. It's a PR2. It's got lots of, it's got a Kinect. You'll see a couple of stereo cameras, a LiDAR. It's cooking popcorn, and it's completely autonomous. what it's done is it's gone off to the internet, it's gone off to WikiHow and looked up the recipe for popcorn. It's downloaded that, and then what it's doing in the sort of autonomous piece is planning all the stages that have to go. It's got the basic stages of how to make popcorn, but there's a lot of other things it has to figure out for itself. It has to be able to figure out where the pot is and recognize a pot. It has to maybe open a drawer to get the pot out. It has to be able to figure out how to turn the gas on before all these kind of things. That ability to have some sort of generic knowledge, we'll call it, embedded on the platform, coupled to the ability to go off somewhere to download the new knowledge that it needs, is going to be fundamental to the way robotics develops in the future, and indeed the way the whole economic piece develops. The way I think about this is like my iPhone. Right, my iPhone tells me how long I've got to go, but it also has apps on it. I'm running one at the moment. And so your iPhone, or your smartphone I should say, becomes useful to you because of the apps that you can download onto it. And in the future, the way robotics is going to go is that you download apps. The knowledge that the robot needs to do stuff, whatever it is, becomes downloadable from somewhere. The hardware becomes increasingly generic. And so we'll see a convergence in hardware platforms in the marine environment, be it surface vehicles or underwater vehicles, but where the real, I guess, intellectual interest, financial opportunity, security concern, all these things is in the knowledge. It's in the sort of embedded planning, it's in the smarts that goes into the robot, and where does that come from? And the corporation that has that, and it may be Google and Facebook and Amazon, or it may be new generations of companies, we don't know. They're the companies that have the power in the way the new generation evolves. So remember this. Remember these predictive words and see if it actually comes to pass. I'm going to finish with Bill Gates, a rather younger-looking Bill Gates than we're perhaps used to seeing these days, because he said it a long time ago. We always overestimate the change that will occur in the next 2 years, and underestimate the change that will occur in the next 10. One day you wake up and suddenly it's all around you, and you did see it coming, but you went to concentrate on something else, or I don't know what happened. These changes are coming faster than you know, and not just in marine, but in other domains as well. And in 10 years' time, it'll be very interesting to see what we're standing up here talking about at a Pugwash event. Thank you very much.